We have the isomerism in the coordination complexes. So isomerism refers to the complexes will be having the same formula, but either their structures or the way of arrangement is different, or if the way of arrangement is same, then the spatial arrangement would be different. So we have two main categories in the isomerism. One is the structural isomerism, the other one is the stereoisomerism. In structural isomerism of the coordination complex, we have four types: ionization isomerism, hydrate isomerism, linkage isomerism, and the coordination isomerism. Whereas in case of stereoisomerism, you have geometrical isomerism and the optical isomerism. We are going to study them in. So we'll study the isomerism. That's a structural isomerism. Here we have majorly four types. One is the ionization isomerism. So what happens here is the exchange of the ligand and the counterion takes place. So if you observe these two, here the bromine is present as a ligand and sulfate is present as a counterion, whereas in the next complex the bromine is present as a counterion and the sulfate is present as a ligand. So exchange of group between the complex ion and the ions outside. So if you are going to ionize it, you are going to get the complex along with the sulfate ion. If you are going to ionize it, you are going to get the complex ion along with the bromide ion. So this is going to answer the silver nitrate test. Since one bromine is outside, it is going to react with AgNO3 to give 1 AgBr, 1 mole of AgBr, and this is going to answer the barium chloride test. So this is how you can differentiate between the ionization isomers. The second one is a solvate isomerism. Here, the exchange of the groups in the complex ion with the solvent. So the solvent can be either ammonia or it can be also water. If you observe these two complexes, here water molecule which is present as ligand is 6 times. There are 6 water molecules which act as ligands, and there are 3 chlorides which are the counterions. So in the next complex, 2 chloride ions are inside the coordination sphere, and 2 water molecules which act as ligands, they have gone outside the coordination sphere. So the number of water molecule which acts as the ligand that differs. And the next thing which we have is the linkage isomerism. Here the ligands attach to the central metal atom through different ways. This is observed in case of the complexes which have the ambidentate ligand. So here cobalt is attached to oxygen which is present in the nitrite group. You can see that. And here the cobalt is attached to the nitrogen which is present in the nitrate group. So this is named as pentamine nitrito O cobalt, whereas this is named as pentamine nitrito N cobalt. So the linkage is through different atoms here. And the next one, the last one which we have is the coordination isomerism, the interchange of the ligands between the cationic and the anionic part. So if you consider the first complex here, this is CONH3 6 3 plus and CrCN6. This is the complex which we are going to take as. So if you see, this is the first complex, and in the second complex, so this is 3 minus, sorry, in the second complex the exchange has been taken place. Chromium comes here and the cobalt goes to the other part. So the interchange of the ligands between the cationic and the anionic entities. Here in the first complex, in the cationic entity, you have the ammonia, and the metal atom which is present is cobalt. In the next complex, in the cationic entity, you have ammonia as the ligand, and the central metal atom is chromium. So the exchange of metals here has been taken place. This is called as coordination isomerism. We are going to study the geometrical isomerism. Here the complexes will have the same formula but different spatial arrangement. In the coordination complexes, we can have two types basically. One is ML4, where there are 4 ligands around the central metal atom, and ML6, where there are 6 ligands around the central metal atom. Here the coordination number is equal to 4, and here the coordination number would be equal to 6. So in case of the coordination number 4 complexes, the shape can be square planar. So if this is a square planar complex, this is a central metal atom. There are 2 groups which are on the same side, and the other two groups are on the same side. So if you write PTNH3 twice Cl2, that's cisplatin, which is an anti-cancerous drug. Here platinum is in the center, 2NH3. You can see that these are the NH3 groups. Both NH3s are on the same side and both chlorines are on the same side. This will give you the cis isomer. And here both chlorines, one chlorine is here, the other chlorine is here. So they are on the opposite side and both NH3s are on the opposite side. So this will give you the trans isomer. When the coordination number is equal to 4, you can also have the tetrahedral geometry. But in case of tetrahedral geometry, geometrical isomerism is not shown because you can see the structures. The relative position of the atoms will be same. So they do not show the geometrical isomerism. If you consider the octahedral complex, its coordination number is equal to 8, you can expect two types of major complexes. One is ML4L2 dash. That means there are two types of ligands. One is 4 times, the other one is 2 times. For example, if this is a central metal atom, that's cobalt, and these are the NH3 groups. You can see that this is one NH3, this is one NH3, this is the other NH3, and this is the other NH3, and this is a chlorine, this is a chlorine. So, two chlorines are on the opposite side. Two similar groups are on the opposite side. This will give you the trans structure. And if the chlorines, two chlorines are not on the opposite side, then this is going to give you the cis form. And in the coordination number 8 complexes, you can also have ML3L3 dash. So there are two types of ligands and their arrangement would be this is Cl3 and this is NH3. So if you arrange this chlorine in the adjacent places, this is going to form a face of the octahedron. So this is called as facial isomer. And if you arrange them in this way, so if you can see this 3NH3, the similar ligands lie on the same plane. So this is going to form the meridional isomer. So the optical isomerism, this is a type of stereoisomerism where the molecule is not superimposable with its mirror image. So if you take your hand and if you take the mirror image of this you're going to get a like this. And if you're going to place this over this, they are not going to merge. So your little finger comes over the thumb. So they are called as non-superimposable mirror images. They are mirror images, but you can't superimpose on each other. So the structural isomerism have the same chemical composition, but the bonds are different here. And when you pass, say there are two isomers, A and B, or say A and A, since their formula would be same. The one is going to rotate the plane polarized light. So the optical isomerism relates to optical activity. The substance is going to rotate the plane polarized light either to right or left. If it is going to rotate the plane polarized light to right, then it is called as dextrorotatory, and if it is going to turn the plane polarized light to the left, then it's called as levorotatory. So optical isomers are said to be chiral. That's not superimposable. A chiral molecule and its mirror image form a pair of enantiomers. That's L and D forms. So the condition for the substance or the complex to show the optical isomerism, that it should be dissymmetric. There shouldn't be any element of symmetry like plane of symmetry or the center of the symmetry. So if you consider this complex where the central metal atom is cobalt and there are ethene 1,2-diamine ligands, which is going to repeat 3 times, and this would be the formula of the complex. So you can write it as CO. And since it's a bidentate ligand, 2 times 3, that is equal to 6. The coordination number is equal to 6, so it should form the octahedral complex like this. And this is En. It's a bidentate ligand, so we are merging 2 bonds with En. This is the first complex with the 3+ charge. Now, if you are going to keep a mirror here, then what you are going to observe is this En repeats here, and this En comes over here, and this En comes over here. Again, this is 3 plus charged 1. So if you compare this, if you take it out and keep it over this, they are not going to impose over one another. So if this is going to rotate the plane polarized light, then this is called as D, or clockwise, and this is going to turn the plane polarized light to the same extent but in the different direction, that's levorotatory. These are, so this complex has no plane of symmetry or center of symmetry, so this will show the optical isomerism. So this is how the isomers are identified. So if you have the formula like M A B C, let this be the formula of any complex. So if they have the same atoms, if there are two structures or two formulae with the same atoms, then they are isomers. If there are no, then they are not isomers. So if they are isomers, you have to see the way they are arranged. Like if they are MABC, if the first complex is also MABC and the second complex is also MABC, then they are, since the formula is the same or the structure is the same, they are stereoisomers. If not, they are the structural isomers. So then you have to see if the B is interchanged, like MABC and MACB. So the ion which is interchanged here, ligand is interchanged, that will lead to the ionization isomerism. If one of them is the solvent or water, then it will lead to the hydrate isomerism. And if there is the presence of the ambient ligand, generally that will be NO2 or NCS, then it will be linkage isomer. And if there are two parts in the complex like this, then it will lead to the coordination isomerism. So if the formula is the same and there is no change or no interchange like this, then they are stereoisomers. Then you have to see if the complex is identical to its mirror image. So you have to take a complex and you have to see whether its mirror image imposes over that. Then if it is yes, then they are geometrical isomers. And you have to see the similar atoms on same side or different side. If they are no, if they are not superimposable, then they lead to the optical isomers. We are going to quickly see the possible number of isomers in case of square planar complexes and the octahedral complexes. So if we have the formula Ma4 where all the ligands are of similar type, and Ma3 B where three ligands are of the same type, then that square planar complex is not going to show any geometrical isomerism. If it is Ma2B2 where there are two types of ligands which are going to repeat twice, then if A and A are on the same side and B are on the same side, then it's called as cis. And if A and A are on the opposite side, two B's are on the opposite side, then it is called as trans. If it is MA to BC, you have to see the position of A only. So if A are on the same side, then it's cis. If A and B are, A and A are on the opposite side, then it's called as trans. If it is MABCD, you have to shift the position of a particular ligand. So you're going to have three isomers possible. So if A is the first ligand, then if B is arranged to the very next, then it's called as cis. And A and B are on the opposite side, then it is trans. A and B are on the same side, then it's cis. So this you can have possible three arrangements for this. So there are three isomers possible. If it is an octahedral complex, then MA6, all the ligands are of same type, and MA5B, that's five ligands are of same type, then this is not going to show any geometrical isomerism. If it is MA4B2, you can expect cis and trans to totally 2. MA3B3, then you have facial and meridional, that totally 2. And MAAB2, where AA is a bidentate ligand. Then you have cis and trans isomers where B are on the opposite side and A are on the same side. Then A, B, C, D, E, F, all the ligands are of different type. Then you have 15 possible isomers. And AB3 where AB is a bidentate ligand. Then you have cis and trans, two isomers possible. And A2, B2, C2. Then you have five isomers possible for this complex.